Hi, and welcome to this video. By the way, we've covered section 1.1 in previous videos. Section 1.1 covered all these different topics that you see in front of you, and we've also covered some exercises related to section 1.1. If you haven't been through these through these videos, I would like to advise you to go and view those videos before you can continue with section 1.2. Section 1.2 covers translating English sentences. Keep in mind that logic has many important applications to mathematics, computer science, and numerous other disciplines. Statements in mathematics and science, and for that fact in natural language, often are imprecise or ambiguous. To make such statements precise, they can be translated into the language of logic. For example, logic is used in the specification of software and hardware, because these specifications need to be precise before development begins, and that's what we're going to see through these examples that we're going to go through in this video. Keep in mind that propositional logic and its rules can be used to design computer circuits, to construct computer programs, to verify correctness of programs, and build expert systems. And software systems based on the rules of logic have been developed for constructing some proofs automatically. Not all of them, but some proofs automatically. So let's concentrate on translating translating English sentences into logic. Like every language, even the English language, okay, is often ambiguous. Translating sentences into compound statements removes the ambiguity, and that's what we're going to see. And also, once we have translated sentences from English into logic expressions, we can analyze these logical expressions to determine their truth values. We can manipulate them. We can use the rules of inference that we're going to study later on, okay, to reason about them. So enough talking, and let's start doing the work. Look at this example. The example says, how can this English sentence be translated into a logical expression? Let's look at the sentence. The sentence says, you can access the internet from campus only if you are a computer science major or you are not a freshman. So the first thing we'll do is we'll start to break this down. Now, one can easily say P can be represented with just the whole statement here, and we're done. But of course, although this is correct, nothing is wrong with it. We can't do much with such a representation. We need to dig a little bit deeper into the sentence and try to build a logical expression through that. So we're not going to represent this as P, but we're going to do it in a different manner. As I said, there are many ways to translate the sentence into the logical expression. Okay, but what we're going to do is we're going to look at the smaller components of this, and then we're going to construct the logical expression. So here, look at the first part of it. Let's look at this simple component. You can access the internet from the campus. So this can be represented, or let's use the logical variable a to represent you can access the internet from campus. Okay. Now let's look at other components that this sentence is composed of. Only if you are a computer science major, so there you go. We got you are a computer science major. This can be another component. So I'm going to represent you are a computer science major with the variable C. Let me write it down. You are a computer science major Okay? Next, we look at the third component. If you look at the third component says, you are not a freshman. Now, we can represent this with a logical variable, but I want to point out something over here, that it's always a good practice to represent the positive form of the statement using a variable. So in this case, I'm going to represent this, use the variable f to represent you are a freshman. Now that we have the three variables identified, let's try to see and construct the logical statement, or the mathematical representation of this statement. So now look over here. You can access the internet from the campus. Identifies the first part of the logical part. Okay. Only if you recall from section 1.1, only if is an expression used to represent conditional statement. So in this case, here we have an implies operator or a connective. Only if you are a computer science major, let's continue. If you are a computer science major, a computer science major would say that, which is represented by the variable c, or then there's another connective, you are not a freshman. Not a freshman can be represented as not f, and of course, according to the sentence structure over here, we see that the access to the campus represented by a can only be granted if you are either one of these. Either you are a computer science major or you are not a freshman. So this logical representation or this logical statement precisely represents the English sentence that is given in example 1. Let's take another example. In example 2, the question is asking me to translate this English sentence into a logical expression. And the sentence says, you cannot ride the roller coaster if you are under 4 feet tall, unless you are older than 16 years old. So let's identify the first component. The first component, you cannot ride the roller coaster. I'll represent it by the variable q, which can be written as, now, you cannot, by the way, as I said earlier, it's good practice to write the positive expression of any sentence or component and assign it to a variable. So I'm going to erase this completely and write q to be the sentence, you can ride the roller coaster. Okay, the next component, you are under 4 feet tall, so I'm going to assign variable r to the statement, you are under 4 feet tall. And continuing with that, the third component is, you are older than 16 years old, so I'm going to say s is defined as, you are older than 16 years old. So we've now identified the three components of this sentence, and we have represented them with three logical variables. Now let's see how we can construct the logical expression that represents the sentence. If you look at the sentence, let me read it again. You cannot ride the roller coaster if you are under 4 feet tall, unless you are older than 16 years old. Look at this if word over here. It's obviously clear that in order to achieve this part, or the left part of the if, you need to satisfy this part. So basically, the left part is the result or the consequence of whatever the right part is. So this if word over here indicates that this is a conditional statement, and the left part is the consequence. The left part is is the negation of Q actually. So we can say that we have a conditional statement with the consequence of not Q. Okay? Now let's see how we can build this conditional statement and build the left hand side of the conditional statement. Just look over here. It says if you are under 4 feet tall, okay, unless now if you are under 4 feet tall means that we are looking for R. The R says you are under 4 feet tall, and it says unless you are older than 16 years old. So now concentrate on the word unless. Now this means that you cannot ride if you are less than 16 years of age. So look at the consequence. The consequence says not being able to ride. This is what the consequence is pointing at. Not being able to ride. Not being able to ride is only the consequence when you are under 4 feet tall and you are not older than 16 years of age, or you are not. In this case, it's going to be the negation of S. This is a logical expression that completely represents the sentence, the English sentence that is given in the example. Let's go on further to example number 3. Example number 3 says, express the specification. The automated reply cannot be sent when the file system is full using logical connectives. Now, just like any English sentence or collection of sentences, system specification also can be represented using logical operators and connectives. Translating sentences in natural language such as English into logical expressions is an essential part for specifying both hardware and software systems. In this example here, we have a software system requirement. Let's see how we can translate that into a logical expression. Over here, it's the same. We're going to do the same thing. We're going to look at some components. So here we have the automated reply cannot be sent, so we can come up with a component. We're going to ignore the not over here, so we can represent P to be the automated reply can be sent. And the next component is when the file system is full. So Q is going to be the file system is full. And of course, now we know that this indicates that it is a conditional statement. It is one of the expressions that is used for conditional statements, and the different expressions that is used for conditional statements is covered in section 1.1. Let me just go over there and remind you with the different expressions that can be used for conditional statements. There you go. No, conditional statements, conditional statements. There you go. And if you can see, these are the different expressions that can be used to write conditional statements in the English language. So then the translation for this statement is going to be as follows. We can say, it says over here, the automated reply cannot be sent, okay, when the file system is full. It's as if we're saying, if the file system is full, then the automated reply cannot be sent. So if the file system is full is represented by P, then the automated reply cannot be sent is represented by not. Oh, sorry, my mistake. That's not the thing. If the file system is full is represented by the Q variable. So it's Q. If the file system is full, this is what the sentence is saying. If the file system is full, which is represented by Q, then we cannot send an automated reply. Therefore, it says we can say that Q implies not P, and this represents the complete the complete translation of this system specifications into a logical representation. Now, this next we're going to look at a set of system requirements and see whether these system requirements are consistent or not. Now, consistency is basically a way to know whether all the three requirements can be satisfied with some truth value for the different components of this. System specifications should be consistent. That means they should not conflict with each other. And this can be used to drive contradictions in system requirements, especially when you are developing software. So let's see how we can prove the consistency of these three statements, or the non-consistency of these three statements. So I'm going to represent the first statement with the capital letter S1, okay, and the second statement capital letter S2, and the third statement with capital letter S3. So we got three different statements, or you can say system requirements, okay. And now I'm going to let's see how we can write them in mathematical form. So first of all, let's identify the small components. Let me read the statements, the three specification statements, so that we can identify the components. The first one says the diagnostic message is stored in the buffer or it is retransmitted. The second one says the diagnostic message is not stored in the buffer. The third one says if the diagnostic message is stored in the buffer, then it is transmitted. So I can see that the diagnostic message is stored is one component. So I can say let P be the statement the diagnostic message is stored in the buffer. Yeah, is stored in the buffer. Let me just continue with this. Okay, so is stored, and let me erase this and go back. Is stored in the buffer, and the next part or component would be it is transmitted, or the diagnostic message is transmitted. So let Q be, and let Q be the diagnostic message is transmitted. Remember, as I said earlier, try to represent the positive form of the component or the sentence with the logical variables. And then next step would be to represent S1, S2, and S3 using logical variables. So now that we know that P and Q are defined like this, S1 can easily be written as the diagnostic message is stored in the buffer, which is P, or, so we got an or over here, that it is retransmitted, so we got P or Q. So S1 is represented with P or Q. Let's see what S2 can be represented as. Read it. When you read it, we'll see that it says the diagnostic message is not stored in the buffer, so not P. Let me erase that. Not P, because the P is defined as the diagnostic message is stored in the buffer. So if it's not stored, then S2 is represented as not P. Let's continue. Now S3. S3 went out of the screen. Oh, there you go. S3 says if the diagnostic message is stored in the buffer, if it is stored, then it is transmitted. This expression gives us the indication that this is a conditional statement, so we can say safely represented as P implies Q. And now we have represented the three statements with using three logical expressions. And let's look at the consistency. What is consistency? Consistency means, or let me write over here, consistent means an assignment of the truth value, okay, that makes all of the statements true. So here's what we mean by consistency. So let's see whether we can find truth values for P and Q such that S1, S2, and S3 are all true. Now I want to make some space so that I can work on. So if you can just be patient with me, I'll just move this down and I'll take it further down. Okay, I believe that's enough place for me for now. Okay, so let's start. Now we want all these three statements to be true. Look at S2. For S2, so we can write over here, for statement 2 to be true, we need not P. See, S2 is not P, not P to be true. If not P is true, this means that P must be false. And there you go. We have found a value for P that makes S2 equals to true. Now, having P equals to false, let's see if other statements can let's see how other statements can be true. So now, if this is the case, then look at S1. S1, which is P or Q, okay, can only can be true. Can be true. Okay. Given that P is false only if Q is true. Right? Let me rewrite it again, or reiterate it. Okay, S1, in other words, let me write over here, in other words, S1, which is P or Q, can be equals to true when P when P is false and Q is true. So there you go. Here is the second value of the second truth value for the second variable, and this will make S1 and S2 to be true. Now let's see. Now that we found that P equals to false and Q equals to true makes the two values S1 and S2 to be true. Let's see if the S3 can also be true using these values. So S3 is P implies Q. Let me write over here. So now let us check if P equals to false and Q equals to true, or equals to true, can make S3 equals to true. So let's check this. S3, according to what we have written over here, it is, S3 is defined as P implies Q. So we got P implies Q. And knowing the values of P and Q, this means that S3 is saying it can be rewritten as false implies true. Remember the truth table for the for the conditional variable, for the conditional operator. False implies true is equal to true. Therefore, we can say therefore P equals to false and Q equals to true makes all S1, S2, and S3 equals to true. Let me take this out of the way because I need more space here. Now we're not done yet, because see the requirement in the question was to find out whether they're consistent or not. So we need our answer needs to be complete, and the way to complete the answer, we can say we found a set of values for P and Q that makes S1, S2, and S3 all have the truth value of true. Therefore, we can safely say that S1, S2, and S3 are consistent. And this is how you make sure that the system software specifications that software engineering give you are consistent and have no conflicts in them. Because if you have conflicting system requirements, then you won't be able to develop the software in hand. So in real life examples, you will have hundreds and hundreds or even thousands of statements like these. If you do linguistical or simple English language analysis to the thousands of statements like these in a real life project, it's going to be a nightmare, and you are prone to have to make mistakes. But if you convert all these statements, thousands of statements, into mathematical representation like this, then using proper software or even doing some analytical steps like the one we have seen over here, you can make sure that these requirements are not conflicting with each other, and that the software that is developed can be developed without any logical issues in the requirements. Now, let's look at example 5. Example 5 is related to example 4, the previous example. Example 5 says, let's add another requirement. And this requirement is the diagnostic message. Let me just move it a little bit so that it comes in the screen. Okay. The diagnostic message is not transmitted. So we're going to add statement number 4. S4 is the diagnostic message is not retransmitted. Okay. Now let's translate this into the mathematical form. Let me scroll back to the previous example so that we get a context of what we have done so far. We have represented P. We have used P to represent the diagnostic message is stored in the buffer. Q as the diagnostic message is transmitted. So in this case, our statement number 4, S4, can be written as not Q. Now let me just rewrite the other statements here again, just so that we can continue with the solution of this. If you recall, statement number 1 was P or Q. Statement number 2 was not P. Statement number 3 was P implies Q. And we have seen previously that P equals to false and Q equals to true makes the first 3 to be true. So P equals to false and Q equals to true makes this to be true, makes this to be true, and makes this to be true. Now let's see if these two values will also make statement number 4 to be true. And of course you can see that since Q is already known to be true, then we have S4, which is equal to not Q, is false. This means statement number 4 is false no matter with this value of Q and with this value of P. So this gives us the conclusion, okay, because we could not find a pair of truth values for P and Q such that S1, S2, S3, and S4 are or have the truth value of true. Therefore, S1, S2, S3, and S4 are not consistent. And this basically is one way or one strategy of identifying the consistency among system specifications. So, now that we've seen how we can translate English sentences into logical expressions, let's see how we can apply the same skills solving logical puzzles. Puzzles that can be solved using logical reasoning are known as logic puzzles. Solving logic puzzles is an excellent way to practice working with rules of logic. And let's look at this example here. Example 7 is related to a type of or family of puzzles about an island that has two kinds of inhabitants, knights who always tell the truth and their opposite, the knaves who always lie. And in this example, if you encounter two people, A and B, then the question is, what are A and B if A says that B is a knight and B says that the two of us are opposite types? So let me just write the facts, rewrite the facts for our convenience. Knights always tell the truth, and knaves always lie. So based on the question, we encounter two people. Person A, let me write that down. Person A says that B is a knight. And person B says that the two of us are opposite types. So let's see how we can approach this and find out who is A and who is B. Let me first of all define two variables, P representing the statement A is a knight, and Q representing the statement B is a knight. In my reasoning, I'm going to use P and Q as a shorthand for saying A is a knight or B is a knight respectively. So instead of writing A is a knight, I'm going to just use P for that, and instead of writing B is a knight, I'm going to use Q for that. So let's look at all the possibilities for person A and person B, and see which of the possibilities conform with the two statements here. So let's start with possibility number 1. Possibility 1. Let's assume that in possibility 1 we will assume that A is a knight. So let me highlight that with a red square here. This is my first possibility. Now let's see. In this possibility, what I'm assuming, I'm assuming that P is true. I'm assuming that A is a knight. Now this means, according to the definition of a knight, that A is telling the truth. So the question is, what did he say? He said, A said that B is a knight. So he said, let me write over here, he said that B is a knight. Now if B is a knight, then this means I've reached to the statement that Q is true. Okay? Now we assume that we assume that A is a knight, and then we came to a conclusion that B is a knight. This means that A and B are of the same type. But this is a contradiction. It contradicts the fact, by the way, this is the symbol of contradiction that I will use. This is a contradiction. It contradicts the fact that if B is a knife, because my conclusion here is that B is a knife, is a knight. So if B is a knight, then whatever B said is not true. As you can see here, B said that two of us are of opposite types. If B was a knight, then A should have been a knave, or vice versa. So this means that my first possibility cannot be the correct solution, or cannot be used to identify, or did not identify the A and B correctly. So let's look at possibility number 2. Possibility number 2. In this possibility, I'm going to assume that B is a knight. So let me highlight that. Now let's see what are the consequences of this assumption. So let me scroll back, show you. So I am assuming that Q is true when I'm assuming that B is a knight. So I'm assuming that Q is true. So I'm assuming that Q is true. This means that B, since he's a knight, he always tells the truth. So he is telling the truth. And what did he say? He said that B is, he said that A and B, or both of us, are of different types. So he said both of us are opposite types. Now this means that A is a knave. Now if A is a knave, this means that whatever A is saying should be wrong. Now let's go and see what A said. A said that B is a knight, which is our assumption, which is true according to our assumption. So this means that A cannot be a knave in this situation. So this is also a contradiction, because over here we are saying that A is a knave, but he is telling the truth about B, that B is a knight. So this is also not a possibility that can identify A and B according to the two statements that were given. So let's look at possibility number 3. Possibility 3, I'm going to assume that A is a knave. And let me highlight this possibility, and let's see how we can study this possibility and come to see whether this identifies A and B correctly. Now, if I'm assuming that A is a knave, so I'm assuming that I'm assuming not P. Now this means that he is telling a lie. If he is telling a lie, what did he say? He said that B, let me scroll back. He said that B is a knight. Over here, as you can see, he said that B is a knight. According to my assumption, if he's a knave, he's telling a lie, therefore B is not a knight. Therefore, B is a knave. Now, if B is a knave, this means that whatever B is telling me is also incorrect. Let's go and see what did B tell me. B said that the two of us are of opposite types. Now, if B is a knave, then this is incorrect. This means that two of us is not of opposite type, or the two of us are of the same type, and of course which is consistent, and this is consistent with what B said, and hence we can see that this assumption is telling us that both A and B are knaves. We should not stop here, but we should go and look at possibility number 4, because possibility number 3, in possibility number 3, I am assuming that A is a knave, and I'm coming to a conclusion that B is a knave. But what about the other possibility, or the fourth possibility? We need to make sure that the fourth possibility is also consistent to this conclusion that we've come to. So let me write the fourth possibility. Possibility 4 is, we're assuming that B is a knave. And let's see if we reach to the same conclusion as we reached in possibility 3 over here. So let me highlight this. This is my assumption in possibility 4. Now, what I'm assuming here is not Q, because Q, if you recall, Q was the statement that B is a knight, then not Q is the assumption that I'm assuming. So if B is a knave, this means B is telling a lie. If B is telling a lie, this means the two, or the statement that he said is wrong, so this means the two of them are not the opposite type. Now, which means that they are of the same type. If they are of the same type, then this means that A is also a knave. And this is consistent with the two statements, and it's also consistent with the third possibility. So there you go. The third and the fourth possibility are the possibilities that are consistent with the situation we have, and hence we can safely say that A and B, so we can say therefore A and B are knaves. Continuing on with our examples of the applications of propositional logic. Another area and field that propositional logic is extensively used is the design of computer hardware. Logic circuits, by the way, they're also called digital circuits, are special kinds of circuits where they have some inputs. You can have more than one input. Okay, so and these circuits then take these inputs and they produce outputs. So you can have one or more output for the digital circuits. Now, for this part of this section, we are going to be concerned with logical circuits that take one or more input, and produces only one output. And examples of that can be seen here. Now, keep in mind that complicated digital circuits can be constructed from three basic circuits. They're called gates. Here's an example. We've got an inverter gate. The inverter gate takes an input bit, say P, and produces the output, not P, or the negation. Remember, when we're talking about digital circuits, we're talking about zeros and ones instead of true and false. So the inverter here, if it gets a signal P, then the inverter is going to change that into a signal not P. So if we get 1, you get a 0, and if you get 0, if you input 0 to this inverter, it will give you a 1, and so on. Now, of course, we can represent that using propositional variables, and it would be the same. The second type of gate is called the OR gate, and it takes two input signals, P and Q in this case. Each is a bit, and produces the output signal P and Q. And the OR gate is represented by this graphical icon. The same way, we've got the third basic circuit is the AND gate, and the AND gate takes two inputs, P and Q, and each of them are bits, and it produces the output of P and Q. And of course, using these three basic logic gates, we can construct more complicated circuits. These circuits can then represent a specific logical expression at the end. So take a look at this example in Figure 2. Figure 2 takes three inputs, P, Q, and R, and it uses a number of basic logic gates. In this case, we're using an inverter to invert Q, the value of Q. Another inverter is used to invert the value of R. And then the output of the first inverter here, along with the input of P, using the second logic gate here, this is the AND gate. It produces the value of P and not Q. And then the output for this, combined with the output of the bottom inverter, is then fed into the OR gate here, and then the output comes out as the logical or the output can be expressed with the logical expression P and not Q, or not R. And this is a very short and simple example on how you can represent use logic gates, use propositional logic to represent logical circuits. Let's take this example. This example says, build a digital circuit that produces the output P or not Q, and not P or Q or not R. So when given input bits P, Q, and R. So what we need to do here. Whoops, screen jumped. Okay, what we need to do here is create a logical circuit that represents this expression. Now, if you recall, in section 1.1 we have seen the precedence operator, operator precedence table. Let me show you that again. On the right side over here, you'll see table 8. Table 8 tells you the precedence of logical operators. According to this table, the NOT has the first precedence, and then the AND operator, then the OR operator, and so on. So we are going to observe the precedence of the operators when we are constructing the logical circuit. So looking at this expression, we see that we have not R, not P, and not R again. So we need a not R, not P to be calculated first. So I'm going to start with the input R, and this input is going to go into an inverter, and the inverter, if you recall, is represented with this graphical representation, and this is going to produce to me not R. So there you go. I have computed this part. Okay, and because the P or not R is between two brackets, this means that I have to calculate this before doing anything else. So let's calculate that. So P is going to be fed to the next operator here, which is the OR operator. So the OR is represented by this gate. So P is going to be fed over here, and R is going to be fed over here. And what comes out over here from here is P or not R. So I have basically covered this first part over here. Remember that parentheses changes the precedence. Parentheses have more precedence than anything else. So let's calculate the parentheses first. Now look in the second part of this. We have parentheses inside. So let's calculate the not P and the not R. So now to make it simple, I'm going to split all these three into something like this. So we need P. We start with P, and to calculate not P, I need to negate it. So we're going to use the inverter, and this is going to produce the not P. And we need to do the inner the inner brackets first. So I need a Q and I need a not R. So I'll start with R and invert it. So we'll get a not R. And I'm going to apply this OR operator with the Q. So I'm going to take the Q and the output of the inverter, and this is going to now produce Q or not R. So we need to now take this and we need to OR it with not P. So we'll take the output for this and we will OR it again, putting it on going through the gate. And here the output is going to be what? Not P or Q or not R. And now I'm going to combine the whole thing together. So I'm going to take the output for this and take the output for this and put the AND operator here, and the output is going to be the whole expression here. From the above input we get P or not R, and from the below we are getting not P or Q or not R. Let me just move the screen a little bit to the right so I can write. And there you go. And this is the circuit that represents this output. And I'm using using this propositional statement. So with this, we finish the coverage of section 1.2. I really advise you to go and do the exercises in section 1.2. The exercises are very straightforward and simple. All those exercises cover the topics that we have covered so far, which are translating the English sentences into logical statements. And the exercises also cover some logical puzzles, which is a great way to practice your logical reasoning. And of course, and towards the end of the exercises, you'll have some questions asking you to convert circuits into logical representation, or vice versa. They will be given logical representations. You'll be asked to convert into circuits. So have fun doing the exercises, and thank you for watching this video.